Okay, so we will begin with concepts of work done. What basically is work done? The definition of work done is product of force and the distance moved in the direction of the force. Let's take a look at the few examples. So the first example is a simple one. Here's an object, a force F is being applied on it, and it moves over a distance d. So the total work done would be force into the distance moved in the direction of the force, as my definition states that product of force and the distance moved in the direction of the force. So the basic formula of work done is W equals to F into D, where W is my work done, F is my force, and D is the distance moved in the direction of the force applied. Okay, so now let's move on to the second example, which is a bit more complicated one. So here's again an object which moves over a distance d, but now the force is being applied on an angle theta to the horizontal. If we say that the total work done on this object is F into d, then in that case, the answer would be wrong. The reason is because the definition states that force and the distance moved in the direction of the force. However, in this scenario, force and distance are not in the same direction or plane because force is at an angle, distance is moving in this direction towards the right, so they're not in the same direction. What we could do is we could find the horizontal component of this force, and using the concept of vectors and vector diagrams, or you could say the resolution of vectors, we could find the horizontal component of this force, which is fairly easy because we know what the angle is, even though in terms of theta, but still we know what the angle is. So applying the formula, cos theta equals to adjacent or base upon hypotenuse. We know what would be theta, any angle, and we know what is hypot, in this case is the force. So F cos theta equals to adjacent or base, and my adjacent or base is my horizontal component of this force. So in terms of theta and force and distance, the total work done would be F cos theta, that would be force, times d, the distance. So F d cos theta would be the work done in this direction on this object. Let's move on to case number 3. In this case, what is happening? That again an object which moves over a distance d in this direction towards the right, but in this case the force is applied vertically downwards on the object. So taking this formula from part number 2, that was F cos theta in times d, and in this part number 3, we could see that the force is perpendicular to the direction in which it moves. Perpendicular basically means at an angle of 90 degrees. So if we just replace the theta with 90-degree angle, so cos theta is equal to cos theta would be replaced by cos 90 degrees, and cos 90 degree is equal to 0. So this value becomes 0. So anything multiplied by 0 would completely become 0. So this tells us that if force and distance moved are perpendicular to each other, then the total work done would come out to be 0. So this was the main concept of work done and 3 different scenarios of work done. Okay, let's move on to the next point, that is the standard notations used in examinations. So we already know that there is a forward force and a backward force. So in order to use the term work done, we would say work done by the forward force, or the other wording could be work done by the driving force or work done by the engine. So these words could be used interchangeably. Okay, then we know that there is a backward force or opposing force. So work done by the opposing force could also be said as work done against resistance, work done against friction. So again, these wordings could be used interchangeably, and it is preferred to use these wordings because these are the ones used in your examinations and again are preferred by the examiner. Okay, now moving on, there is a small note again, which is um, similar to the law of conservation of energy, which says that in mechanics, work done always gets converted into some form of energy, which is why work done and energy have the same units. The first part is similar to the law of conservation of energy. Like again, this says in mechanics, work done always gets converted into some form of energy. Law of conservation of energy stays the same. It says that energy can neither be created nor be destroyed, but rather it changes from one form to another. So again, what I wrote is work done always gets converted into some form of energy. So the forms of energy in which work done is converted into are the change in kinetic energy, 1 upon 2 mv square, the change in gravitational potential energy, mg delta h, and heat energy, or work done against friction. So there were some examples on how to calculate work done and work done being converted into different forms of energy. So let's start with example number 1. We have an object that is traveling on a slope. The object travels with a constant speed. The distance of the slope is basically 16 meters, and the forward driving force is 30 newtons. The slope is at an angle of 30 degrees to the horizontal, and the height of the maximum position of the object is 8 meters from the ground. The mass of the object is 20 kilograms, and assuming the acceleration due to gravity is 10 meter per second square. The question says calculate the work done in moving the object from A to B. So how are we going to calculate? So again, from the previous video we saw that work done can be divided into kinetic energy, gravitational potential energy, and work done against friction. And basically, we have to find the change in Ke, the change in GPE, and the work done against friction. So let's move on. The change in kinetic energy. What would be the change in kinetic energy? It would remain zero. The reason is, again, from the previous part of this chapter, we saw that when constant speed is maintained by the object, the change in kinetic energy is always zero because the initial velocity and the final velocity is zero. So the value of the initial kinetic energy and the final kinetic energy would also remain the same. And so subtracting similar values will give us zero. As a result, the change in kinetic energy would be zero, again because constant speed is zero, so change in velocity is zero and change in kinetic energy would also be zero. Now we have to find the change in gravitational potential energy. The change in gravitational potential energy could be found out by mass of the object times acceleration due to gravity times the change in height. So the mass of the object is 20 kilograms, acceleration due to gravity was given to be 10, and the change in height as seen in the diagram is 8 meters. And you would argue that why not 16 meters and 8 meters? Because in calculating gravitational potential energy, we always see the vertical height and not slant heights. So the vertical height, that is the change in vertical height of this object, is 8 meters. So that is the reason why we would take 8 meters instead of 16 meters. So by calculating and multiplying the values, we would get the answer of 1600 joules. Now the next part is to find out work done against friction. So work done against friction is done by the simple formula, that is W equals to F into D, where F would represent my frictional force and D is the distance that is traveled in the direction of the force. So as we know that friction is again in this direction backwards because object is moving forward, so the friction force that is being applied would be in the reverse direction or backwards direction. So work done against friction. So we know that there is a frictional force of 30 newtons and the distance traveled is 16 meters because in the direction of the force. So and it is against friction, so we have to find it out. And the answer would be 30 newtons times 16 meters, and the answer would be 480 joules. So the total work done in moving the object would be the sum of the individual delta Ke, delta GPE, and the work done against friction. because delta KE was 0 and GPE is 1600 joules. The work done against friction is 480 joules. The total work done in moving the object is 1600 plus 480 plus 0, ignoring the 0, and my answer is 2080 joules. Now, moving on with the next question. The next question says that again, the object is moving at a constant speed. The forward driving force is now given to be 9,000 newtons. The weight of the object is 2,000 newtons. The slant distance or the distance of the slope is 40 meters, and the vertical height of the object at maximum position from the ground is 12 meters. The question says calculate the energy lost or energy dissipated as heat. That is basically find the work done against friction, because again what we did in the previous slide was that heat energy or work done against friction, because usually heat energy is referred in kinematics and in movement of objects, and in work done heat energy is usually the energy that is lost. So again, when object moves they produce heat heat energy due to friction, and so that is a loss in energy. Okay, moving on. Again, work done could be divided into three types of energies. That is, change in kinetic energy, change in gravitational potential energy, and work done against friction. Okay, so the change in kinetic energy in this case again would be zero, and I guess I don't have to tell this again because from the previous two parts we know that when there's a constant speed, the change in kinetic energy would also be zero. And there would be a change in gravitational potential energy, and the reason is again because there is a change in height and the vertical height, because as we could see from the diagram it says from 0 it goes to 12 meters. The vertical height of the object changes from 0 to 12, so the vertical height that is changed is by 12 meters. So again multiplying, and again what is m and g? We were given the value of mg because weight of the object is equals to mg. So the weight of the object was given to be 2000 newtons. So the value of m times g will also be 2000 newtons. So we could just replace the value of 2000 newtons with mg, and change in height is 12 meters, and we could just multiply and find out the change in gravitational potential energy. And in this case it would be 25,000 joules or 24 kilojoules. Then the third form of energy is work done against friction. Okay, so how would we find out what is the work done against friction? Because the question itself said what is the work done against friction. So the easy way out is, again, we know that work done is distributed into three forms of energy: change in kinetic energy, change in gravitational potential energy, and work done against friction. We know the value of kinetic energy, change in kinetic energy. We know what is change in gravitational potential energy, and we know what is work done. Why? Because we know what is the forward driving force, that is 9,000 newtons, and we know that the distance that is traveled by the object, that is 40 meters. So we could easily calculate the work done on the object. That would be F into D, where F would be my force or driving force, that was 9,000 newtons, and the distance traveled was 40 meters. So the resultant answer would be 360 kilojoules. And my formula could be framed like this. We knew that delta KE plus delta GPE plus work done against friction was equals to total work done. So to find out the work done against friction, we could just rearrange the formula to make it work done against friction is equals to work done, the complete work done, minus change in kinetic energy minus change in GPE. So by rearranging the formula and the values, 360, the total work done, minus delta KE is 0, so we could ignore the 0, and subtracted by the delta GPE, that was 24,000 or 24 kilojoules, we could get the answer of work done against friction, and that would be 336 kilojoules. Alright, so let's move on to the next set of example, and in this case, yeah, and this is again a bit more complex example. So yeah, example number 3. The question says that initially the object travels at a speed of 2 meters per second. As soon as the object reaches its final position, it has a speed of 80 meters per second. The distance of the slant height is 30 meters. The frictional force is 600 newtons, and the vertical height of the object in the maximum position from the ground is 8 meters. So the question says, calculate work done in moving the object from A to B. Again, the work done is divided into three forms of energy. Number one, change in kinetic energy. Number two, change in gravitational potential energy. And the last one, work done against friction. Again, change in kinetic energy is again due to the change in velocity of the object, and final kinetic energy of the object would be 1 upon 2 m into v square, where v would be the final velocity, and it is given to be 18 meters per second. Then subtracted by 1 upon 2 m into into v square, that is where the velocity would be the initial velocity given as 2 meters per second, and the answer would be 3200 joules. The change in gravitational potential energy would be mass into the acceleration due to gravity times the change in height, and the mass is 20 kilograms as given in the question. 20 kilograms. The acceleration due to gravity is 10 meters per second square, and the change in height is from 0 to 8, so 8 meters. And put in the formula mg delta h, and we will get the answer 1600 joules. Then for the work done against friction, we know that frictional force is 600 newtons. The distance traveled is 30 meters. So we just multiply using the formula W equals to F into D, and 600 times 30 would give us the answer 18,000 joules. And as we knew that work done is the total work done is the sum of delta KE, delta GPE, and work done against friction. So we just have to add these values up, and the total work done would be 3200 plus 1600 plus 18,000, and this comes out to be 22,800 joules of total work done on the object to move it over a distance of 30 meters by overcoming a force of 600 newtons, and by increasing its velocity from 2 meters per second to 18 meters per second, and by displacing the object by a vertical height of 8 meters.